Hello everybody, today we're going to talk about chemical reactions in this unit 4.1 to 4.4. We'll be doing this in two parts, so watch out for part 2 of this video. The first one is going to be introductions for chemical reactions, and we're going to touch upon net ionic equations as well. So before we start on this, you really want to make sure you understand the idea of physical and chemical changes. So whatever I'm looking at a physical and chemical change, I'm always looking for things that are involving breaking bonds or changing the phase of matter. So if I take a look at a physical process, what I'm looking for is how is that physical process being affected if I am changing a couple of properties. Normally this involves what I call intermolecular interactions, and what those interactions involve is IMF forces, specifically things like dipole-dipole, hydrogen bonding, and whatnot. So if you think about a physical process, you're basically looking at properties that are changing, but you're not looking at the change in composition. And the classic example of this is you're doing a phase change. As an example, solids to liquids or liquids to gas, you are moving these particles apart, and by doing that you are changing the actual property of the material, but you're not really changing the composition of it. So water vapor is still considered to be water if it's in a gas form versus in a liquid form. However, in a chemical process, it's a little different story because now we're rearranging the bonds together. So whenever we break a bond or we're forming a new bond, what you're really doing is you're creating a new substance in the process. So if you ever really wonder about what a chemical change really represents, it represents when you're actually making and rearranging these atoms versus a physical where you're not actually changing anything. Now the gray areas are somewhere in the middle. And the best example of this is when you're dissolving any sort of solute, such as salt in water. And the reason why it's in the middle is because technically it's a physical change and not a chemical change, because you can technically remove the salt from the solution and you're still getting that, but at the same time you are breaking bonds when the salt is breaking apart into its ion form. And so when we're really talking about anything that dissolves, you really have to think about this definition of a chemical versus a physical. If we are breaking a bond, it's technically a chemical. However, if you can't get the material back, then obviously it's still a chemical process. And so we're talking about ion dipole in that case. And so if you think about a crystal lattice structure in a salt particle, every time it breaks apart, it actually releases these ions, and these ions are free floating. But the fact that remains that we broke those ionic bonds. So in this case, it's more of like somewhere in the middle. So solubility is a little tricky story. I would consider this more of a gray area, but more leaning towards the chemical phase if I were to define it by bonds. Now, in terms of the way you represent these, is you always want to talk about IMF forces. So if I take a look at this solid as an example, and I'm looking at nitrogen oxide, monoxide, what you're looking for is the arrangement of these particles. So on the left hand side you see a positive negative charges in a solid form, very similar to like salt as an example. But the moment they start moving around, you begin to change the phase of the matter, but still NO. The difference here is that you're having this ability for the liquid to have these intermolecular forces being rearranged because of whatever reason that's being put in. Now usually that would mean applying some heat, or it could be involving putting it in some sort of solution for that matter. Now if you're making a solution as an example, here is something where I really want you to think about and pause this video to take a look at this, because many people still need to understand this effect. When you're getting a polar solute, something that dissolves in water, what you're getting is that these rearrangement of these ions are now being attracted by water. And what water does is, because it has a 2 negative charge dipole moment on the oxygen, it will attract itself to form an aqueous solution. So this is considered to be a physical process, and as I was explaining in the previous slide, it's not that gray area that we're really talking about, but technically it's a physical process. Even though we're breaking apart the bonds, what we're really doing is we're attracting those ions into water. So NH3 is a classic example of something where you have a polar solute, it's being put in water, and then it's forming this aqueous solution. So chemical processes really involve breaking apart and forming new bonds. So again, making that point very clear, this usually happens both with ionic and with covalent bonds. And the substances transformed can have different properties. Example is color changes, temperature changes, formation of precipitate, which is any material that's not soluble in the solution. Color changes as well, as I mentioned, and also chemical change. So these are all indications that chemical processes have occurred. In other words, the atoms have rearranged themselves. So I want you to really think about chemical processes as this formation of new product. Here's a classic example of a chemical process. If we take soft metal, and sodium is a very, very reactive metal, by the way. It's in group 1 of the alkali metals, and usually it has one valence electron. But what it does is that if you form that with chlorine gas, you're going to make table salt. And as a classic example, if I were to ask you to draw this out, the way you would draw this is that you would put the sodiums compacted together because it's a solid. The gases are diatomic because chlorine exists as a diatomic gas, and then when you rearrange them, you're going to form table salt. And table salt is going to be a solid. So that's the reason why table salt is very strong. It's because the atoms have rearranged themselves in such a way to form this crystal lattice structure. So the gray area we're talking about earlier was when you're starting to dissolve stuff, right? So if I take solids, NaCl, and I put it around that, what you're really doing is that you're involving breaking these ionic bonds and you're forming these ion dipole. Now, where is the ion going to be? The ion's going to be where the Cl is at, and then your dipole moments interactions are going to be where the hydrogen is being attracted to. And by doing that, you're going to surround the chlorine molecules with H2O and the sodium as that by breaking apart those bonds. Now notice carefully that the H2O does not break. So it's really what we're talking about is this ionic bond where these attractions force the salt to actually break its ionic bond structure. Now let's talk a little bit about combustion reactions, because combustion reactions are also another part of this whole chemical reactions phase. If we're talking about chemical reactions now or chemical changes, the classic example is going to be methane or CH4 adding with O2. And what you're seeing here is this idea that if you add O2 molecules to CH4, the CH4 is going to rearrange itself to absorb that O, or that O is going to take that C, however you want to look at it. By doing that, you form water vapor molecules. And so if you take a look at the equation, it's going to be CH4 for the methane plus 2O2 gives CO2 and 2H2O. Now, as you can see from here, the one thing is that this equation is balanced. You got one carbon, and where did the carbon get the CO2 come from? It came from the original carbon. Also, you're going to see that you have those 2O2 molecules in addition to that water, which came from the methane. The law of conservation of mass states that whatever I have on my left is going to equal to whatever's on the right. So if you take a look at the masses for each one, you can kind of see that the AMUs are all going to be the same. If you take a look at the right-hand side, you can also see that the carbons are the same and everything. So we should get the masses on the left equal to the masses on the right. So let's talk about balancing a chemical reaction or chemical equation. Now, if I take a look at carbon plus CO2, I'm going to be making carbon monoxide. Now, as you can see from here, if I actually go ahead and do this equation, I'm going to have to figure out how to deal with this O2 here. So the way we do it is that we have to create two COs. So if you think about it, whatever's on the left has to equal to whatever's on the right. By creating two CO molecules, I'm able to balance this out. Problem here is I only have two C's and only have one C right here, so obviously we're going to need two C's. By doing that, now we figure out the balance equation. So we have two carbons, one O2, and CO. Now the general idea here is that you have to understand that O2 exists as a diatomic molecule. In other words, it's always bonded to another O. And once you combine them together, you're going to make your two COs. In other words, it's a 2-to-1 ratio. Two carbons make to one O2 make it two COs. Alright, so here's a little refresh about how to balance equations. Hopefully you guys already know how to do that, but I'm just going to give a refresher here. So the first thing is you're going to write the chemical formulas for all the reactants and products. You're going to balance the elements that do not exist independently first by adding the coefficients. So in other words, there's molecules out there that don't exist at. Then you're going to balance the elements that exist independently last, and then finally check to make sure that both sides are balanced. So let's give you an example here to just kind of get started. So if I take a look at this, this is called the molecular equation. Okay, so, well, they actually want you to write the molecular equation. And as we can see from here, this is an unbalanced equation because we have a methane, we have an O2, CO2, and H2O. Now, as you can see, we have one carbon here, but the hydrogens are not balanced. We have 4 here, 2 here, and here we have 3 versus 2. So the question is, which one do we start off with on combustions? So what we're going to do is we're going to first start off with the waters, right? because that's the one that gives us that first rule. So we're going to go ahead and balance out the two H2Os first, and that gives us that. But by doing that, now we're going to have 4 oxygens. So what we're going to do is we're going to add the 2 oxygens right here. And now we pretty much have your carbons. So if you take a look at this example, I usually like to go with the waters first. From there, go backtrack into the other one so that you can go ahead and make life a little easier and then figuring out how the carbons are going to look. Now, balancing net ionic equations, it's a little bit different, but again, the idea is still the same. You want to have the same number of moles on the left with the same number of moles on the right. So let's take a look at this example. Write the balance equation for ionic for the reaction that takes place when aqueous barium nitrate is added to an aqueous sodium sulfate, and then barium sulfate precipitate forms. Okay, so the first thing you want to do is when you're writing these net ionics is that you really want to know your polyatomic ions. So if you don't know what sulfate is, pretty much can't do that. Same thing with if you don't know what barium is or sodium. So the first step is we're going to write out the actual reaction. So barium nitrate is going to be here, and we balance that out with the 2 because barium has a 2 charge. Sodium nitrate has -1, and it's going to be an aqueous solution because they've stated that in the problem. Sodium sulfate is another aqueous solution, so it's Na2SO4 aqueous. Now when you actually do the ionic, what you're going to do is you're going to assume that they are breaking apart into the solution. So I take the barium nitrate, since it is soluble, it's going to be Ba2+, and it's going to be 2NO3. Now how do we get the 2? It's because there's 2 nitrates in there. Now same thing with sodium sulfate. You have to know your solubility rules. So sulfates are going to be soluble. Now if you take a look at sodium here, and especially if you have a group 1 like Na you have in there, now what you're going to have is 2 Nas because we got the 2 in there, and then you got 1 of the SO4s. Now moving along for next ionic, what you're going to have here is Ba2+, 2NO-, and the reason why we do that now is because we have to be able to cancel out whatever is on this side. So if I break this apart into its aqueous form, what I'm going to also do is break this apart into its ions. So 2+, 2NO3 because we got 2 moles of that, 2 Nas, and that plus your barium sulfate, and then you end up with 2NO3 and 2Na. Now the reason why we put a barium sulfate is here is because we know that if you take a look at barium sulfate, it's not going to be soluble. So you got to take a look at these rules when you actually are doing a double replacement reactions. And so earlier I did mention that it doesn't help, but again, that's the assumption. But if you want to double check to see if these ions are going to form, barium sulfate is not. And so that's the reason why we have a solid there. Now 2NO3, that's soluble, and 2NO3 is soluble. So by doing that, we're going to cancel out whatever is on the left with whatever is on the right to balance net ionic. And so our final equation is going to be technically the barium. And these do not include what they call spectator ions. So these are called your spectator ions because they don't really participate in the reaction. What they're really doing is that they're in there, but they're not really creating any sort of substitutes because they both dissolve in both the product and also in the reactants. And so our final equation is going to be Ba2+ because we write them all as ions. I write down SO4 as an ion because it's an aqueous, and then we form the BaSO4. All right, so if we're taking a look at barium nitrate, I think we did this one, we kind of take a look at that. So a net ionic equation only shows the reaction that took place. So normally we're used with dealing with a problem that only involves precipitation. So if I ask you write a net ionic, what I'm really referring is just to barium sulfates. However, a complete ionic shows all the species will be present. So if I go ahead and write that out, usually you have to include both the spectator ions and the species. And that's basically would include something like what we saw earlier in the other one. So here you would not cross out those ions. Most of the time what you're going to find is they'll ask you for the net ionics. And what's going to happen there is you have to know your solubility rules. All right. Make sure you pause this video and watch the solubility rules because there's going to be a lot of them coming up.